Good morning, everybody. This is Tejendra Singh. I'm I work at UCLA Office of Advanced Research Computing, and today's topic of presentation is the transfer learning across heterogeneous structures for large-scale structural health monitoring purposes. The speaker is Dr. Hissam Soleimani. I hope I pronounced it correctly.
Yeah, perfectly. Yeah,
He's
thanks.
a postdoctoral fellow in civil engineering department. And let me talk a little bit about him. He's a postdoctoral fellow in civil engineering department at UCLA Engineering. He holds PhD in civil engineering and an MSc in computer science, both obtained from Virginia Tech. And his research has always been at the intersection of these two areas. So, without much ado, let's welcome Sam. That's how he goes with. So, all for you, Sam.
Yeah, thank you. Hello, everyone. I hope everyone is doing fine and well. And again, thank you for the complete introduction, Tajendra. I really appreciate that. So, yeah, I can go directly to the presentation and see how it goes. Okay, so let me turn on my pointer just in case. So today I'm going to talk about transfer learning across heterogeneous structures for large scale structural health monitoring purposes. So first of all, let's see why structural health monitoring. When we're living in like an urban environment, there are several services that has to be provided to us. Like we need places to live, we need transportation, we need recreational like facilities, we need energy. So all these needs in an urban setting actually require some infrastructures. So we may need buildings, we may need bridges, wind turbines for energy, and so on. The list goes on. So any failure in these infrastructures can have severe impacts on the people, on the society, and probably it will cost some money and also discontinuity in the services. So we can merge all these problems that an infrastructure failure could cause into socio-economical impacts. So structural health monitoring are the tools to avoid or lessen or mitigate these impacts by monitoring the infrastructures. So traditionally, for example, we know that, transportation, large bridges are important, dams are important. So traditionally, visual inspections was the tool to actually perform the health monitoring on those systems. Some experts are dispatched and they go and take samples, take pictures, look at the structure, and see whether is there any superficial uh, features that somehow convey there's like a damage or something. So we have that for bridges. We have that, for example, you can see that people are taking pictures from these tendons to see if everything is correct or not. And so this is the traditional SHM. On the other hand, we also have the data-driven SHM. Instead of having the people to go there and do the job, we have some sensors. So we put like accelerometers, S-strain gauges, even thermometers and whatsoever features, whatsoever sensors that are required, and we install those on the structure to actually do the structural health monitoring remotely. So as you can see, it's obvious that data-driven SHM has some very obvious benefits. And one of those is that there's no need to dispatch people to go and do the monitoring task. We can do everything online in an online fashion, and with the data just comes in by internet or something. So by the Internet of Things. So it's much easier in a way. Data-driven SHM. So for the data-driven SHM, what they do actually is that if we have the building, if you have the bridge or this infrastructure, they put some sensors on structure that I mentioned, accelerometer, strain gauges. And what they got is just some signals. So for example, the sensor output can be, as I mentioned, acceleration, temperature, and other things. And with this signal, instead of the traditional like inspection, Primarily, the SHM just wants to identify if there is a damage or maybe prognose the damage, localize the damage, and also perform the severity measurements. These are the main goals of an SHM model. So for doing that, I mean, having this data, there are several different approaches on how to use this data to perform the SHM. So one of them is system identification. So system identification, what is also called in the domain as digital twins, are like that. We have a bridge, we have a building, and we also have like a physical model of that, like for example, the finite element model or any sorts of uh, other like framework that we can simulate the behavior of that structure. So for example, if we have the bridge, then we can actually build like a finite element model outside of that bridge. And we use that finite element model to see when the bridge is starting to have some problems. So because this finite element model, for example, is fine-tuned to perfectly align with how the bridge performs, if we get some suspicious output of the bridge, then we can check it with the finite element model to see if there's like any problem or damage or something. And as you can see, this approach is case specific. I mean, if we have a breach and if we just create like a finite element model for that breach, that means we can just use it for this structure. We cannot go out and use this system for a building or something. We have to build it from scratch. We have to fine tune and the digital twin again from the scratch. So the other approach that we can use the data to perform SHM is actually pattern recognition. So for the pattern recognition, which machine learning are very like super famous tool to do that. I mean, the process is simple. We have the data, we have the labels, we can do it supervised, we can do it unsupervised and solve the problem. But I'm just talking about like classical machine learning approaches. So signals, as you can see, for example, for this like exemplar picture here, are very noisy in nature. They're very highly dimensional. So for example, with the decision trees, we cannot make like classification for these noisy signals with 10,000 dimensions, 5,000 dimensions. So there are some ways that people solve this problem. So one of them can be like dimensionality reduction. The others can be to select a feature by ourselves. So for example, we say, okay, maybe the 90% percentile of, for example, the amplitude of this signal is a feature. And then we feed that feature into like a clustering, like decision trees, random forests, and whatsoever, and we perform the analysis because the data is hard to grasp for like a simple model. So again, here we have some case specificity. So the reason is that, I mean, aside from that, we need to train a model, we need the data. Again, some of those feature selection by the user can make these models case specific. On the other hand, we have representation learning. So what I can also call it like the deep learning. So inside the deep learning, there is no need for us to, okay, go see, okay, this is a bridge. I guess these are the important features. And so let's train a machine learning algorithm based on these features or something like that. It does everything automatically. So I just run like a very quick literature review by myself for the papers that was published on Elsevier, which you can actually access through Scopus. And you can see if we actually look at the keywords before 2016 about all the SHM studies that I could retrieve, you can see that there are some classical words here, like operational model analysis. So operational model analysis is like a tool of system identification. For example, Bayesian methods, support vector machines. I mean, these are like famous machine learning approaches. But if we look at the literature from 2016 onward, we can see that the neural networks, machine learning, even physics guided, physics informed learning, which is top here. I mean, the color is not like super clear. So all these things have replaced those classical models. I mean, we have like, uh, I'm just looking for some a small classical model, but I cannot even find them. So that's, I mean, there's a reason for that. And the reason is that the representation learning offers more generalizability. So, I mean, whatever structure you have, if you have the data, I mean, you can just the same neural network. I mean, for example, you can just build its convolutional based neural network and just apply it to like different structures because they do the feature extraction by themselves. So this is the power of the deep representation learning. But now that the deep learning allows us for some more freedom in dealing with the data and structure, is there any way for us to scale the SHM benefits? I mean, if we look at a single structure, SHM, as I mentioned in the second slide, can help with cost efficiency. It can extend the lifespan of the structure. I mean, if we diagnose a problem in the structure way ahead in time, then we can fix it and then we can avoid the whole collapse of the system and so on. So, but can we scale that, for example, to an urban region? I mean, we have like 50,000 different structures. Is there a way to do that? Because if we do that, aside from scaling all these features to an urban environment, we can do other additional analysis. Like we can have rapid post-event assessment. We can have more like modularized resource allocation. We can have disaster prevention and mitigation. But the problem here is to how to obtain that generalizability that's to go from just one structure and scale it to like a whole urban environment. And these are the things I call the barriers. So we have the deep learning. Deep learning has like a so strong capacity. But again, data dependency and model dependency, again, let's somehow suppress the generalizability of the deep learning model because we do not care about the features anymore. We do not care about some specificity in the structure to design features and other things. But we still need data, and we still need to train a model for each of the structures that we have to perform the SHM to see whether the structure is normal or abnormal. What would happen if we actually reduce the data dependency and model dependency? We can reach an ideal model. I mean, an ideal model in my viewpoint is a model that, it doesn't require any data, it doesn't require any model fine-tuning, tuning, and whatsoever. So we can just apply it between a structure A and a structure B. So we can move towards that model by reducing the data dependency and model dependency. But for sure, we have to be careful about the costs and benefits. I mean, if you come up with some model that doesn't need any model fine-tuning, but it requires lots of data, I mean, that doesn't solve the problem. We have to see the costs and benefits and to see the trade-off of whether this approach actually worth it or not. So how we can reduce these dependencies? I mean, so what I was talking about, like deep learning till this point was just like traditional deep learning. I mean, just applying some deep neural networks to some structures and something. But for reducing those dependencies, we have to think of some extra steps, some changes, some modifications, or some or finding the niches in which those deep neural networks can solve some of the SHM problem with a specific design or something like that. So let's say that we have a building, we have a frame. So the damage on this frame can happen at any point. So for example, it can happen at this brace, it can happen at that column, it can happen at that beam. So what we usually do, as I mentioned about data dependency and model dependency, is that we know where these damages, I mean, we have somehow predefined where those damages can occur. We actually make those damages happen, and then we somehow put some sensors there, extract the data, and we extract it for like undamaged condition of the structure, damage type 1, damage type N, and something, which is in a supervised SHM manner. So here is what I mean by dependency. I need to know where are the damages, and I have to also capture data from those damages. But can we somehow go around this? I mean, can we solve this using some deep learning strategies and design? And the answer is yes. I mean, there are tools out there. So for example, we have generative adversarial networks. The generative adversarial networks are pretty famous and are most useful for their generation because they can generate some realistic, based on what we are actually giving it, outputs just out of random noise. So if we just give it noise, for example, we are just producing some fake or unreal like digits, and we have the real ones, and the discriminator learns to judge between these two images to see which one is fake and real. And at the end of the day, the generator becomes very capable of generating data that are very similar to the real data. I mean, that's usually how they use GAN. I mean, in GAN, no one cares about the discriminator, but we can actually use this design to circumvent like the need for data for the SHM purposes. Like, for example, this is something that we've done in this research. That's we have the just the normal condition of the structure as the input, and we give it to the GAN. So what the GAN does, I mean, for example, this is one real output of a structure. So what the GAN does, the GAN from just a random one-dimensional noise, by going iteration by iteration, it can learn to produce some signals which are very similar to the normal behavior of the system. But we do not care about that. We care about the discriminator because on the way to learn those generations, the discriminator actually learn what is a normal condition of the system and what is not a normal condition of the system. I mean, any fake data that was generated by the generator is like a damage by itself. It's a signal that is different from the undamaged condition of the structure. So at the end of the day, the discriminator can be used as a damage detector because if you give it a signal, it can judge between, okay, this signal is from the normal condition of the structure, or probably it's conveyed there is some sort of problem or damages in the system. But this is not enough. I mean, we still need to train a GAN model. We still need to like capture enough normal condition of the structured data. So it's time to look at this problem from a different viewpoint and actually try to set up a roadmap to actually see how we can reduce those dependencies as we have sought. So let's say we have a source structure, and from that source structure, we have many data. I mean, this is like benchmarks in computer science. So for example, we have ImageNet, we have other databases, and we have everything from this structure. Maybe it was done in a laboratory setting or something. So we can use this data to train a pre-trained model. But at the end of the day, in the urban setting, which we are trying to propagate our models in, we might have another structure. We might have like a frame, which is the target structure. So the question is, what is the way to just apply this pre-trained model to this target structure? I mean, the solution is transfer learning, right? But here we have many more complications. We have many more criteria to be met. And but those criteria, I mean, every structure is like a data set by itself. So for example, you have pre-trained your model on ImageNet, and now your task is to identify, I mean, cats from dogs. That's like a separate building. If I give it a second building, the whole fine-tuning should be done. Each building is like uh, a classification task by itself. So we want to reduce this. I mean, if we want to just use transfer learning as it is, okay, we have a structure B, we have a structure A, we just fine tune the model. But that doesn't work because if we want to apply the SHM on like an urban scale, we have to have no fine tuning or new trainings involved. And also, one of the other objectives we have is that, I mean, the methodology that we come up with shouldn't pose any limitations between the source and target domains. Like, for example, we have a bridge, we have a dam, we have like a traffic mast arm. I mean, it shouldn't make a change. And also, it should be time effective, which I will talk about it later. And the most important one is that it should function in a zero-shot setting. I mean, when we have a structure and we just put the sensors there and we want to start structured monitoring to work, the only data that we have is the incoming online data. We have no information about the possible future damages that may happen in the future. I mean, those are the things of the future. So it should be zero shot. So by having these four objectives, I know that we have to go in the way of transfer learning to actually achieve like an urban scale SHM applications, we can start to reducing those dependencies and move towards this model. So here I will first talk about one of our recent research, which is called zero-shot transfer learning in SHM. So as I mentioned, we have a source model and we have a target data or target data that we want to apply the source model on. We want to use transfer learning. But we have to consider that we shouldn't have any, it shouldn't contain any training or fine tuning. It should be time effective. It should be zero shot. So fine tuning is ruled out. So what the other option is? The other option is to use domain adaptation. So in domain adaptation, you don't have to fine tune your model. Your source model remains the same, but you tune the target features in a way to be applicable, I mean, to be readable by the source model. But in defining that domain adaptation strategy, we should make sure that it's time effective and it should be zero shot. But how to achieve that? I mean, there is a whole branch of like deep learning, which is called physics informed or physics based deep learning. And there is a reason that the people goes after the physics of the problem because physics are generalizable. So for example, I mean, if you talk about like simple physics problem, for example, throwing a ball or movement of ball in a drop scenario or something like that, I mean, you have the formulation. I mean, it's always generalizable. I mean, you have a parametric model, you have a function, and you can apply that function in any situation that meets actually the condition of that function. So that's why if we resort to the physics of the problem, there is a good chance that we can improve the generalizability of the deep learning models. So let's say that we have an input-output system A. We just give it an input and it produces an output. If the output is time variant, like for example, a signal that changes over time, we can analyze that output using the power spectrum density. Or I should better say using the digital signal processing. So the domain knowledge here is digital signal processing. And we can use the power spectrum to see and define what is actually inside that output. So for example, if the output is just a combination of two simple sine waves, if you draw the power spectrum or the power spectral density, this would be the power spectral density. It shows you that at which frequency lines, I mean, which frequency harmonics are actually contributing the most to the signal. But how we can use this power spectrum density to help the transfer learning and domain adaptation? The way is if the inputs are the same, and this model is a whole black box model. This is like the building. We have the inputs, we got the output from the sensors, and this is just a black box. This is just a structure. If the inputs are the same and outputs are the same or comparable, then we can reach the conclusion that these two systems are the same without us even knowing a simple thing about those systems. In SHM, the good thing is that the input is white noise. I mean, it's ambient vibration. It's just a flat spectrum. So if we have a source SHM system and a target SHM system, if the power spectrum density of these two structures are equal, so we thus claim that if we have a model that works on the source and there is a transformation in which we can make the power spectrum density of the target equal to the source, then the same model would apply to the target. So this is something that we claim. And we do that transformation by using domain adaptation, but a domain adaptation that requires a specific feature design to go towards those harmonies and power spectrum density. And also we have to design a neural network, a deep neural network that can accommodate those features. And it must be time effective and it also should be zero shot. So I'm gonna show you a glimpse of the results here. So let's say that we have a model that was trained on a benchmark on a source structure A, and now we are applying it to like the target structure. You can see the impact of the domain adaptation that we designed. So for example, if we just use a model that was trained on the source to the target, I mean, this is just a damage detection 0, 1, and we compute the mean area under the curve for the ROC curves here, we can see that it is just slightly better than a random guess. But if we use the domain adaptation, we could see that the same model without any fine tuning could reach like very super high area under the curve for the SHM damage detection that we have here. But going back to the source of the problem, why we do not have generalizable SHM tools. I mean, so for example, in the field of natural language processing or the field of like images, I mean, we have huge data sets. And with the power of like contrastive learning and all those innovations, we can reach large zero shot models. So for example, maybe like ChatGPT wasn't trained on your specific question, but it can answer that because it has been trained on a large corpus of data. That's the reason. But in SHM, if that is the ideal representation, I mean, ideal benchmark data set for the SHM, that we have damaged and non-damaged data from like super huge number of structures, the fact is that we do not have that. If we have that, then maybe we could also try to go in those paths. I mean, just use some super transformer architecture and learn everything from this data set and then apply it to every structure we have. But the problem is that these are just the available data. I mean, most of the data is missing. We have very few benchmarks. And as I told you earlier, as I mentioned earlier, each building on itself is like a whole new branch of data. I mean, so that's why we have like many blurry parts in this like ideal representative SHM data set, and the most parts are missing. So when the most parts are missing, what we did in the previous research was using transfer learning to go into each of these sections to see to perform the transfer learning in SHM. But the fact is that since it was a zero-shot approach, and actually we have several benchmark. I mean, this benchmark doesn't give us like a whole representative SHM data set, but at least it gives us like a I mean, if you use several structures, source structures, compared to just using one source structures, I mean, the benefits are obvious. So we made a claim here, and we said that we have we haven't redefined it, but for our research, we redefined the meaning of damage. Damage is actually any divergence from the current status of the system. I mean, if the system is intact, and if we go to damage class number one, okay, we removed one brace of the structure. We can also look it in the other way. I mean, if going from undamaged to damage is like adding a damage to that part of the system, we can say that the no damage is also a damage from the viewpoint of damage number one, because we made a change to that brace. We actually put that brace on its place again. And we can also say that about all the damages. So for example, if we have damage number one and damage number two is also a damage compared to damage number one, because first we have to fix damage number one and then we have to inflict damage number two. So by making this assumption, we can perform multiple transfer learning. I mean, if we have like a source structure here, it has like 5 different damage classes. By defining a deep ensemble learning strategy, we can use, I mean, this whole SHM data set is not representative, right? But we can at least use whatever that is inside here by using deep ensemble learning. And we can actually see that in this comparative table, which is about 3 SHM benchmarks called the yellow frame, QUGS structure, and Z24, we can see that by using the multiple sources, we can enhance the results as compared to just using a simple source here. So there's information out there, and we have to include all of those into the pipeline to add more generalizability to the transfer learning in SHM. So now we get into like what's actually the title of this paper says about the SHM in heterogeneous structures. So earlier we discussed, and with the pictures I showed you, we have buildings, we have bridges, but we might have other infrastructures. I mean, as simple as a traffic mast arm or even a rotating machinery. I mean, maybe at some parts of a factory or some places, we have these machines. These are called the rotary machineries. And actually, the SHM problem in the rotary machinery is called fault detection. I mean, those are literally the same. There are some infrastructures, and they get damaged, and we have to identify those. So we are here, as you saw earlier, the representative SHM dataset does not exist, and we have some sources. And we saw that if we combine these sources, the results would be better. But is there any way to move from rotating machines to structures? Because if we do that, it's like that we have added additional like benchmarks to this blurred image here. So we can actually further enhance the results and get better results for the SHM. So, I mean, these two structures are evidently different. I mean, this is just a rotating machines going into a gearbox, and this is a frame. So how we can do that? So for doing so, for actually getting help from fault detection and adding to the structural health monitoring, we have to resort to contrastive learning. And why we have to do that? Let's say that this is the hypothetical rotating machinery feature space. So instead of learning what a feature is, what the contrastive learning does is that the contrastive learning puts some anchors. I mean, inside its training regime. I mean, we have done a bit of a different contrastive learning here, but in a sense, you can see that the contrastive learning puts some anchors and tries, without having any labels, to merge or to keep together the data that looks similar to each other around those anchors. So we can use the contrastive learning in the rotating machinery space to find the damage path. Like, for example, for the rotating machinery, which are small, which are easier to create data set out of them, we can define those damage paths. So we can have damage path to the damage X, we can have damage path Z to damage Z. So by building that feature space, then when we actually transfer the target structure using the very domain adaptation that was talking earlier to this feature space, it doesn't really matter what are the types of the structure, how the feature, how the damages happened. We can actually see that the target's non-damage data and the damage data, how the damage is diverged from the non-damage data, from the transformed non-damage data, based on different damage paths that we have here. So by doing so, we are hoping that by just using the rotating machinery data, for example, we can do the SHM for a bridge, or we can do the SHM for a frame. And as you can see, it actually works. So let's say that, again, those two friend benchmarks of us, like yellow frame and the QGIS benchmarks, you see that I have a performance here, which is called supervised. It means that I have that infrastructure. I have every damage data, every non-damage data, and I actually trained a supervised model for that. I mean, this is like the optimal thing. I mean, if we have the power and resources to just and data to just train SHM algorithms for the whole buildings in an urban environment, then we should probably have gone with that. But that's not possible because we do not have the data. So this is like the utopia. This is like the utopian performance or something. And we can see that by ensembling rotating machines and ensembling all of the data that we got from the rotating machine, we can get really close to what we can get from the supervised accuracy. Like, as I told you, supervised is like the best. I mean, we can get like 0.998, but we can actually reach 0.99, about 0.99, by using extra benchmarks that the rotating machines gives us. So using heterogeneous structures, what it does is that it helps us to further improve or further expand the data sets that we have the SHM, with the ultimate objective of like having the scale SHM to an urban environment. So is the future research? So what I just said till this point was just about structural damage detection. And as I mentioned earlier, for a full SHM, we need to have damage localization and damage severity measurements. So these two, I mean, these are very hard tasks because, so for example, we said that we have no information of the target structure. So how we can localize the damage without any like historical data? I mean, these are very hard tasks that we are currently working on, but actually this is how the research about like our urban scale SHM is moving forward. Yeah, that's the end of my presentation. I'm so thankful, and if you have any questions, I would be more than happy to answer that. Yeah, thank you.
Thank you, Sam.
Sure.
So, it's open for the question and answers. Please come online, and if you have any questions, feel free to ask. Anyone?
Yes, I guess we have something in the chat. Great presentation. Thanks. Yeah, thank you.
Good. So now I can ask one question. So you covered this the structure which is stationary and one which is rotating.
Yes.
What about the structures that may be just oscillating, not the rotating, or something linear motion, for example, trains or something like that?
Yes, that's something doable. I mean, the reason that we went after the rotating machines is that the rotating machines have like a large body of literature about fault detection. So I mean, the fault detection problem in rotating machines is very famous. So when you say that I could do the transfer learning between rotating machines and actually the buildings and the structures, that gives people an idea of how well the methodology is working. But I mean, and the other reason is that as I told you, it's a very famous branch of research. So we have like lots of data sets. But for example, for a linear system or an oscillating system, probably we should look into like what sorts of research they're doing, like SHM related research they're doing regarding that. And if the data set and the benchmark is available, I mean, that's a very super suggestion because we can expand this territory. We can expand the representative SHM dataset area or region. And that's something very useful. And I would probably think about it. I mean, thank you.
Thank you. So, if there is no more questions, let's thank you. Thanks, Sam, for the wonderful presentation.
Yeah,
And
sure.
hopefully, we'll see you all next time in the next presentation, which will be in February sometime. And hopefully, you have a great rest of the day.
Yeah. Thank you, everyone. Thank you for listening to my presentation. Have a good one. Yeah.
Thank you.
Bye.
Bye.